Okay, working. Okay, very good. Yeah, well, thank you very much for inviting me to my favorite subject. This, and we've been working on gamma colliders since for the past 5 years, revisiting the whole idea, and we've been working on center mass energies between 125 GeV and 10 TeV. But I was asked to also consider 100 TeV. So at the end of a configuration for at 100 TeV as well. So after introducing the gamma collider concept, I'll talk about the Higgs factories, and then a recent Delphi's analysis of the Higgs management at 280 and 380 GeV. I'll discuss a little bit more then about the accelerator and machine detector interface, the technical challenges, and then multi-TeV gamma colliders. So Compton colliders, where the laser photons are upconverted to the energy of the colliding electron beams, have been studied for more than 40 years. And starting with this paper by Ginsburg and Telnoff and others, and but usually in the context of initial, supplemental, or follow-on stages of E plus minus colliders. Recent innovations in photon science, particularly in XFL technology, though can lead to enhanced capabilities. And so the previous collider concepts were limited to optical wavelength lasers due to the nascent status of the XFELs, and what I call an underappreciation of the particle physics advantages of running the gamma colliders at shorter wavelengths. Also, another reason for still considering gamma colliders is that the E plus minus collider proposals continue to be developed by cost. And so as an alternative, gamma factories are of interest. They have a smaller footprint due to the fact you don't have to produce the additional Z boson. And then the physics case for XFEL versions of gamma colliders is more compelling than the previous optical laser colliders from 20, 30 years ago. Finally, another reason is if at 10 TeV Wakefield E plus E minus collider is not feasible due to the positron acceleration, the XFEL Compton gamma configuration of a 10 TeV Wakefield collider, electron collider, may provide the optimum particle physics environment for such a machine. In that case, a XFEL Higgs factory would serve as a prototype for that. So just to remind you what is involved in this example, the numbers are taken from our XFEL concept. You have an XFEL laser beam, or a laser beam in general, colliding with the electron beam with the energy that you want to convert to the photons to, and then you have and then when that out of the Compton IP comes not only the desired photons that have been upconverted from the electron beam, but also you have a spectrum of other electrons and you can have positrons and photons as well. You have the same thing from the other side, and they collided the primary IP, which in this case is 60 microns from the two Compton IPs. The photon luminosity is very simple. It's the electron geometric luminosity times the Compton conversion efficiency squared. You optimize the electron beam luminosity using electron beam deflection like you do at any linear collider, and then you maximize the Compton conversion efficiency. And the tool that we're using for this is the Kane Monte Carlo, written by Hikaru Yokoya, and actually most of the talk results come from an analysis of this, what's shown on the slide here, namely the Compton IP collisions followed by the collisions at the primary IP. That's the really solid part of this talk, and I'll discuss the other things that have to be studied to bring this thing closer to reality. I want to go a little bit into detail about the X variable in gamma colliders, because that enters in many different ways. The X variable is defined to be 4 times the electron energy times the laser photon energy divided by the electron mass squared. It's essentially the center mass energy of the electron beam and the photon beam in units of electron mass squared. The center mass squared in units of electron mass squared. The relation is the maximum Compton photon energy is this x value divided by 1 plus x, so that as x grows larger, you gradually your maximum photon energy approaches the electron energy. Another important feature is that the angular spread, the angular divergence of the photons, is proportional to the square root of the of x, so that whereas many things get better as x gets larger, this is one thing which does not, and necessitates a very close space between the Compton IP and the primary IP. Important thresholds in X that I'll be discussing at X equals 4.82, the threshold for the high energy photon that's produced initially by the Compton collision, the interaction of that with a laser photon to annihilate, to produce a E plus minus pair, that opens up and that depletes the high energy photon beam and adds positrons to the mix of particles that are exiting the Compton IP. At X equals 8, you have the trident production, E gamma goes to E minus, E plus, E minus, and that has interesting and different consequences at different gamma gamma center mass energies. And then in the figures I'm going to show, there's a parameter kappa that's 1 minus the probability for a Compton photon to annihilate with a laser photon. And this parameterizes the depletion of high energy photons. So I'll start. I'm going to now take the variable x and move it beyond the threshold of 4.82. So this is a example of a spectrum of the luminosity at the maximum value of x before the pair production turns on. It has an effective cross section for Higgs production of 250 femtobarns, which is roughly the cross section for a plus or minus the ZH at 250 GeV. Now, if you go up in X, the peak gets narrower, but this kappa that parameterizes the depletion of high energy photons, that's now gone from 1 down to 1.25, and so you have you've degraded your total photon luminosity, and the effective cross section has gone down to 40 femtobarns. This continues as you go from X from 20 to 40, 80, 100. It plateaus at 100, and then things to pick up a little bit. And by the time you get to X of 1,000, the peak is so sharp that it compensates for the loss of photons in their annihilation to E plus E minus pairs. And there's kappa of 0.11. You can actually increase kappa by changing the sign of the relative sign of the electron and laser polarization. That opposite sign helicity suppresses the gamma gamma to E plus E minus, and so you get an overall and even a cross section of 311 femtobarns. So in general, there are advantages. There are disadvantages. Things become more complicated once you go above these thresholds, but there are advantages in that you get a peak structure that's more like an E plus E minus a collider instead of a spectrum like I had for the optical lasers. Let's discuss a little bit the Higgs production cross sections for gamma gamma minus and mu plus mu minus. So as I mentioned, so the E plus minus the ZH is about 310 femtobarns. Mu plus mu minus annihilation is with no polarization is 7 times 10 to the 4 femtobarns, and of course the E plus minus is minuscule. The total gamma gamma annihilation, if you could narrow the beam to the point that's within the width of the 4 MeV width of the Higgs is 3 nanobarns. Of course, you take full advantage of that because you can't possibly produce a beam width that small. But in general, as you make the gamma gamma beam width narrower, your Higgs rate will go higher, as we just saw in the previous slide. And then there's also gamma gamma goes to double Higgs. On this slide is shown in green is the E plus E minus to Z Higgs cross section as a function of kappa lambda, the standard model value being at 1, and then the cross section dependence on kappa lambda for different gamma gamma center mass energies, 280, 380 GeV, and then in gold the 380 GeV with the full gamma gamma luminosity spectrum folded in. So there's at the standard model value of 1, the gamma gamma cross section is roughly double that of E plus minus to Z Higgs Higgs. You have a kind of a production dependent, a cross section dependence of the on kappa lambda that's similar to that at gluon fusion at LHC. It's just that the peak, the dip has been shifted from 2.3 down to 1 due to the presence of both W and the top in the loop. So the Photon Collider concepts, they've been developed in the 2000s. They can produce similar numbers of Higgs bosons per year to E plus E minus, but with higher backgrounds. And so we've been investigating this higher X value with a X-Phil-Compton collider that we call XCC. Okay, I'll discuss a little bit more in detail that schematic. Well, no, yeah, right now. So the proposal that we had for SNOMAS was a 4 kilometer long footprint, 2 Linux with a 40 millivolts per meter baseline and an upgrade to 120 millivolt per meter to get you from to the full 380 GeV. Halfway down the LINAC, you divert every other bunch to produce the X-Phil light, and you have also in the baseline design, you have a cryo RF gun that's not been designed yet, that has incredibly low emittance and high brightness, and then you have Kirkpatrick Bayes mirrors to focus the X-Phil light to a very small spot right in front of the detector, and so they're focused at the Compton IP. The choice of the XCC design parameters, what value of X was chosen, the Higgs rate actually continues to grow with increasing X. See here, before it was 311 at X of 1,000, by 4,000 it's 1,200, and then 5,000 by the time you get to X of 16,000. How did we choose the value of X? Well, we imposed the condition that the XCC Higgs rate be comparable to the ILC's rate at 250 GeV. We then iterate with X-Phil experts on what photon wavelengths and energy and pulse energies are possible using an E- beam with up to 62 GeV to drive the X-Phil, and then the Kane Monte Carlo is used to calculate the Higgs rate. And to maximize the geometric luminosity, we assume a round beam for the 62.5 GeV E- beam. That means that the beam spot will be a few nanometers in both the horizontal and vertical. Also, things like the laser waste scanned, and here you can also see the different effects that the Kane Monte Carlo includes: linear Compton, and then the nonlinear QED processes, as well as the trident process. And then also the bunch length is varied, the beta functions varied, all to determine what the optimum set of parameters within reason. And so we end up with the X value of 1,000 and which is the KeV photon. So in the lingo of X-Phils, that's a soft X-ray. Shown here is the analytical calculation I've shown before. Then on the bottom is the Kane Monte Carlo simulation. It includes something that wasn't included before with the analytical calculation. That's the beam strong gamma luminosity that you see below 100 GeV in the center mass energy. A comparison of the optical versus X-ray laser Higgs factory luminosity spectra. So on the first of all, for the optical laser, one had to run with 216. Okay, so I'm taking now the final design from the middle of the 2000s, before the second interaction region was removed from the ILC design, and gamma collider interest fell off. With that design, they had a 1 micron laser was used. For that, you had to go to 216 GeV in the E minus center mass energy to produce the maximum luminosity at 125 GeV. And so you can see the spectra there for the signals on the left and the backgrounds on the right from the optical lasers versus the X-fill. And then at 380 GeV, again, the spectra for X-fill in black and the optical laser in red. We've recently completed and about to publish a Delphi's analysis of gamma goes to Higgs, assuming the SID detector in a full suite of backgrounds. So this includes all the E gamma, E plus, E minus, all the processes that you see in this this diagram on the right for the X-fill design. The event display on the right kind of indicates a possible advantage of gamma versus E plus, E minus, where you don't have to contend with the Z boson in the E plus, E minus analysis. You have separate analyses for each Z decay mode. That's not needed. We don't know yet if quantitatively that has improved things, but it's qualitatively you can see that perhaps it can lead to some advantages. And then the results are shown here. On the left-hand side, the different components, signal and background before the final neural net cuts, and then afterwards on the right. Ultimately, a 10-year run gives an uncertainty of 11%, 8.5 significance. And then that can be converted into a limit on delta kappa, which, okay, so just the nature of the gamma cross section in double Higgs on kappa lambda is such that the dip or the slope goes to 0 is very close to the standard model value of 1. But outside to the left and right of that point, the precision is about 6%. The sigma versus kappa lambda curve at 280 GeV is intriguing. It has a narrow valley at kappa lambda equals 1 and a steeply rising walls. And that provides great leverage in converting cross-section area to kappa lambda. So we've, without having analyzed the other decay modes, we just assumed, well, okay, the typical error with respect for the cross-section from the BB bars represent the other decay modes that error is representative of the other decay modes. And so we extrapolate the 11% error with just BB bar, with just 4Bs, to a 6.4% error at 380 GeV. And then convert that back to 11% given the rate of given the Higgs rate at 280 GeV versus 380 GeV. And we get this gold curve shown here, which asymptotically goes to about 4% compared to the FCCHH, which is 2.5%. And it's interesting, the two colliders, they have a different weak spot, and with the gamma collider at 1 and the FCCHH at 2.3. Well, 380 was the our first choice because it was the maximum in the gamma goes to Higgs cross section with respect to center mass energy. But what really matters for the for your triple Higgs coupling sensitivity is the slope in this curve of sigma versus kappa lambda, and it's much steeper at 280 GeV. And so really, that's, I mean, we're going to, having done 380, we're going to go back and do 280 GeV because we think that's just a much more favorable center mass energy for the triple coupling analysis. Okay, for the linear collider facility, you can combine the 550 GeV results shown in green with the gold result for gamma at 280, and you get the blue, and then you get the blue curve shown in this plot here. Okay, that's the and then for the quartic coupling and triple Higgs production, No work has been done. It's just noted that the cross section at 500 GeV in triple Higgs is roughly the same as the new triple Higgs coupling in E plus minus at 3 TeV. There are other gamma studies to be explored, are shown in this table here. Going back to this beam parameter table, it's the emittance is very aggressive at 120 nanometers. Beta star is very aggressive at 30 microns. Bunch length is a very high current through the accelerator, and they have round beam final focus, which is distinct from the usual flat final focus designs that have been studied for the past decade. Furthermore, the electron beam must be 80 to 90% polarized to achieve the results that I've shown. For the XFEL, the design from the XFEL experts has been validated with the full Genesis program, which is the top of the line full simulation of X-ray free electron lasers. At 380, even more aggressive emittance, beta star bunch length, just really can't imagine it being attained now, but it's assumed it could be reached once the 125 GeV design is realized in the spirit of an upgrade. And there's no design for the XFEL at this at 380 GeV. This just shows an initial final focus design with the round beams. The idea is right now is that you have Kirkpatrick Bayes mirrors placed as close to the IP as you can. Of course, they have to be very stable, so there's no way they're going to be inside the detector. They're going to be placed just outside. And this example, they consist of two 5-meter long mirrors, one for the horizontal focusing and one for the vertical. And then the mirrors are contained in a vacuum chamber. And at this point, the electron beam is also going to be passing through the chamber. And so these are all things that have to be studied in detail just to even see if it's feasible. As far as the machine detector interface is concerned, the environment is fairly similar to that of E plus E minus. The incoherent pairs are flux is roughly the same. Here it shows perhaps the inner radius has to be moved out a little bit compared to an E plus E minus collider. What's really unique though is there's a moderate flux of soft KV X-rays in the central region, and so you have to add a few tenth of a percent to a percent of radiation length of heavy element to the beam pipe for cosine theta less than 0.8. The absorber increases to 5 radiation lengths at 0.93 and above. 0.95 is a very complicated design. So in our Delphius analyses, we just cut off the detector and make it blind at cosine theta greater than 0.95. Okay, design challenges. To get to the 40 megavolt meter is essentially done. That's C-band room temperature accelerator. It's in hand right now. But what's needed for to go to higher energy, you need a higher gradient, something like C cubed. And then the polarized low emittance E minus injector is needed unless you want to install a storage ring. And then one has to look at the focusing of round beams to 5 nanometers. I mentioned the production of and focusing of nearly a joule per pulse. Just so you know, the currently the XFELs that are running, for example, SLAC and DAISY right now, the maximum soft X-ray energy per pulse is a few millijoules. So this is roughly 300 times the current operating soft X-rays. There's been a preliminary study of the mirror parameters, and for example, mirror damage limit using a boron carbide as the coating. Looking at mirror reflectivity, And the conclusion is that very large mirrors are needed much longer than 1 meter that are produced with FEL quality today. Okay, now let me just go to the a little bit into the multi-TeV gamma colliders. So in this study, you just take what we've done before and replace the 62 or 190 GeV electron beam with a 5 TeV Wakefield E- beam and simulate the gamma collisions using the Kane Monte Carlo. I'll be showing results for two different types of machines. One was a parameter set from a particle Wakefield accelerator. The others from a laser driven, and but there's really no. What really sets the two apart are the beta functions. One is an aggressive beta function that we used before, 30 microns. The other is 100 microns. That's really the difference between the two results, which I will show. So starting now with this 30 micron design, the very aggressive high geometric luminosity design. And just start out with x equals 4.8 and adjust the parameters to get 100% conversion, like sort of what was done in the past for gamma colliders. There you end up with a very high nonlinear QED parameter, c squared of 50.2, and you have various nonlinear effects leading to this the photon spectrum on the right once you've turned on the nonlinear QED effects, and then the total luminosity spectrum with respect to this gamma center mass energy looks like this. You can dial back the pulse energy to get to remove the strong nonlinear effects, and then you get a spectrum that looks like this. But you have lost the you have lost the peak at the highest values of 15 TeV. So try X of 40 to get more of a peak in the spectrum, then you get something like this. But this is with no beam Strömling or coherent pair production included. And once you do include it, you find that the Kane Monte Carlo shuts down. One can get around it by adjusting the parameters, and you end up then with, on the right-hand side, with the spectrum of the gamma luminosity spectrum shown on the right. And what's happening is that the coherent pair production is eating up the high energy photons and produces many positrons that actually end up pinching they pinch the E- beam, leading to the higher fields and even more coherent pair production. So it's kind of a runaway pair production that's taking place, and amazingly, you have pinching of E- beams. That was seen by Kane. That's been validated now with more sophisticated programs like WarpX. Actually, this is Kane showing how certain slices and longitudinal slices, the width of the beam is much smaller than the geometric width, both for electrons and for positrons. But at 1 keV, this does not happen. The fields are not as high, and what the reason is that the trident process, E gamma goes to 3 E's. Electrons undergo that scattering so many times that their energy is much reduced, and the EM fields in the collision are 3 orders of magnitude smaller. And so, strangely, for a different reason, X-ray lasers actually seem to give the highest luminosity in the top 20 or top 10% of the the gamma center mass energy. And so this is now a summary 10 TeV of different conditions. So you have E plus E minus without any Compton collisions, both with the higher beta of 100 microns, and for the low beta of 30 microns. so the green is the photon spectrum that you get just colliding electrons together. The magenta then is with the smaller beta. And then two examples of Compton gamma colliders. In blue is the higher beta, where you don't have this runaway pair production taking place, or you can run with lower photon energies. And then the gold is the 1 keV, 1.2 keV configuration with the small beta. So for the small beta, a minimum value of X is required to minimize the final electron energies through this multiple trident interaction. And after that, the optimum value of 90,000, or around 1 keV, that's determined by the Compton IP evolution of the processes, the Compton scattering, the trident, and the gamma goes to plus or minus. It's interesting that even though the X value is very different from what we saw at 125 and 380, the same photon energy, about 1 keV, provides the optimum peak luminosity. And finally, at 100 TeV, I just take this talk, I just took the parameters of the machine shown earlier and just increased the energy from 10 to 100 TeV, and then ran it through Kane to see what many different times to see what sort of parameters would work. It's kind of the same story as was for 10 TeV. For the type focusing, a minimum value of X is again required to minimize these final D minus energies. But then after that, again, the X value of 600 was determined to have the optimum 10% luminosity in the peak. However, here the laser pulse energy has increased from one joule, which is we've been using for everything I've shown before. Now it's gone up to 20 joules due to just the extremely small cross sections at this value of X. And what's not included, we know through in the backup slides, we know at the X of 90,000 used here for 10 TeV that the trident process is still the dominant process, and E gamma goes to E minus plus N different E plus minus pairs. Those other, so this is E minus plus N equals 1 E plus minus pair. N equals 2, 3, and 4 are above this threshold, but their cross section is still negligible compared to the trident. But at 100 TeV, 600,000, I don't know, I haven't studied that. And but it's again interesting that the optimum peak luminosity, again, another very different X, still shows up at around 1 keV. That some scaling laws that would demonstrate that still have to be shown. So summarize that the XEC, and we just touched the surface. We went first to the gamma goes to double Higgs, because that's sort of the measure by which colliders are judged these days. But the gamma goes to single Higgs at 125. What advantages there are running on a resonance like that versus E plus minus Z Higgs? Still looking forward to investigating. But with this X spell versus instead of optical, the XCC has a compelling Higgs physics case, and it's just for the minimal 4-kilometer foot. Furthermore, this 1 keV seems to be the best for 10 TeV, 100 TeV scale colliders. It would serve as a prototype of that collider, those Wakefield colliders. In general, with this X-fill gamma collider, the problem of cost size has been created and transformed into a series of technical challenges. The high brightness polarizing minus sources, the focusing of the round beams of 5 nanometers by 5 nanometers, the layout of getting the 4 beams in and out of the interaction region. These are things that still are not known. and they need, we have proposals, get money to study them, but we need the accelerator R&D that's unique to XCC, the production of close X-ray beams is unique not only for this, but also within the broader X-ray science community. XCC is the first science to require a dual pulse soft X-ray beams, and these could ultimately have broader applications. This is something we think the photon science doesn't yet know that they utilize. Not quite true, but approximately. And this for XCC, high brightness electron acceleration and high power. Yeah, so this is sort of the collection. You could have a complete heat factory program at 125 and 280 or 380 PV. It could be either a standalone project or part of a linear facility as an interaction. Yeah, that's there. Yeah, but
thanks a lot. Questions? When you say second interaction region here, it means what precisely? Maybe this is not clear to me.
So the ILC had one interaction region because it was felt that was a cost-benefit decision early on to reduce the cost. And the new Collider facility said, no, we're going to go back to two interaction regions. And one possible utilization of that would be for a GAN-GAN Collider.
Sorry, they usually insist on the fact that they had to do this push and pull, and so there was one interaction point. Maybe I'm confounded by the.
So the Collider facility abandoned the push pull. It says there'll be two interaction regions, perhaps 2 E plus or minus, or perhaps we've been studying because of the advantage of the polarization. We've sort of always thought. Again, we utilize 2 electron beams, but really with the 60% positron polarization, we're now looking into simultaneously running E plus and minus. Simultaneously running E plus minus collisions with the photon collisions. So you don't have to reconfigure one half of the collider to run electrons. So. So it'd be 2 interaction regions, one of which is the possibly gamma.
But still, it's the same geometry. One interaction point in the middle. It's the same usual geometry. One interaction point in the middle. Maybe you manage to split it.
Two interaction points.
So how does it work?
Well, you can just draw it on the sheet. There's already a crossing angle, and you can. Sorry. You can see it drawn on the sheet of paper that you have 2 interaction regions per.
Okay. And I guess I have to admit that a lot of this is very new to me, and to an extent, it used to be so new for me on colliders, but there is more to learn apparently. So maybe I should ask the same question I asked to Vladimir before. What's the size of accelerator experts working on this right now? Because we learned it's a very big, important number to know. And at this stage, all of this looks very interesting. You showed plots to very high energies. The chance that it goes on shell in part is correlated to the amount of people that can actually work on this. So I'm trying to figure in my head, not how realistic is the physics, but how realistic is the R&D for a project like that to go somewhere.
Well, that's what we're working hard on. I mean, I just, so we proposed one lab-directed research and development proposal last year. We sent it to the wrong division, to the to the fundamental physics division, rejected outright. This year we more properly sent it to accelerator division. It got through the first stage. Waiting for the final result whether or not we'll get the funding. It's black, and then we're also looking. We're seriously looking into other sources of funding outside of the DOE laboratories as well, just to get this thing off the ground.
So let's say tomorrow somebody arrives and gives you a 10 TeV or even 100 TeV E- beam. Let's suppose this is solved. What is the next big challenge that you need to, I mean, technological challenge that you need to solve to make a 10 TeV or 100 TeV photon collider? Yeah.
Okay. So when at 100 TeV, we really need to understand the additional processes that are present in the Compton IP with such large electron photon center mass energy, x of 600,000. And also, well, the other problem is that, okay, remember, current X-ray technology and solid X-rays with a few millijoules, and we're trying to study how we have one design to produce a joule for pulse energy, but now this 100 TeV requires much more, like 20 joules. So R&D into how you
So the power of the laser.
Such high power, such high pulse energy. Among many things. But we have fundamental problems we haven't yet solved. At the lower energies. Bringing the beams in and out of the IR, we don't. There are two possible processing methods. One is the 2 milliradians, in which case you build the aperture of the final focus large enough, everything that exits the collision passes through that aperture. But if you can't do that, then you have to go to a larger cross section, 20 milliradians, 30 milliradians, just like in the past gamma collider designs. And then even at 125 GeV, it looks like the flux is such that you need the collimator between the IP and the final focus. So we've got to first solve these problems at 125 GeV before you can think about the 100 TeV.
Is there anything you could do with FCCEE?
FCCEE?
Yeah.
This Compton process in storage rings, I just don't see how maybe Vladimir is studying these things more generally, but the disruption of the beam is so great, I don't see how possibly be used in a storage ring. I mean, have enough imagination. What's one proposal? Do you use
So the one proposal probably come from your group too. In FCCE, the topic of collimation of the beam is extremely important, and how to get rid of the hollow particles is challenging. So one of the ideas was if you create a laser beam, X-ray or laser beam, with hole inside. Basically, it's a laser beam which has a kind of circular profile, right? So, right, and then particles with larger amplitudes will touch the light, will see the light, and particles in the hole of the light beam will not see it. And those who see the light and collide with gammas lose so much energy that they very quickly end up in the momentum collimation system because of Compton interaction. These electrons or positrons will lose, due to the same process, a lot of energy, will end up in the collimator very quickly. So, and this is non-destructible and nor laser collimator.
Yeah, so
Yes.
yeah, it's using lasers for collimation as one application, yeah, at FCCE.
Okay. I don't see other comments, questions. So I think we can call it a day. Thanks again. Thanks to all the speakers of this afternoon.